In the quiet heart of Copenhagen, in the late 19th century, a world of ideas was about to be born inside the mind of a young boy who would one day redefine the language of physics. Niels Henrik David Bohr came into the world on October 7, 1885, during a time when science was undergoing a silent revolution. The world had just begun to grasp electricity, radio waves, and the deep mysteries of the atom. But for the Bohr family, curiosity and intellect were not mere subjects of study, they were a way of life. His father, Christian Bohr, was a respected professor of physiology at the University of Copenhagen, known for his groundbreaking work on respiration and blood circulation. His mother, Ellen Adler Bohr, came from a family deeply rooted in education and culture. Together, they created a home where scientific conversation mingled with music, art, and philosophy. In this nurturing atmosphere, Niels Bohr's mind began to awaken. As a child, he was not a prodigy in the dramatic sense. He was quiet, observant, thoughtful. But behind those calm eyes, there was a depth of curiosity that sought not just answers, but understanding. He was fascinated by the patterns of nature, the ripples in the pond when he threw a stone, the resonance of sound when he struck a bell, the shimmering reflection of light in a window pane. Each of these small wonders ignited a question in his mind, a need to see what lay beneath the surface of the ordinary. To Niels, nature was not simply to be admired, it was to be decoded. Growing up in an academic household, Niels and his younger brother Harold were encouraged to explore and reason. Dinner table conversations often revolved around ideas, not possessions. Christian Bohr believed that a child's curiosity should be guided, not constrained. He would often challenge his sons with open-ended questions, not to test their knowledge, but to stimulate their reasoning. Harold, who would later become a distinguished mathematician and Olympic footballer, shared a close bond with Niels. Together, they built experiments at home, tinkered with instruments, and tested the boundaries of what they could observe. Their father's laboratory was not off-limits, it was a playground of discovery. Copenhagen, during Bohr's youth, was a city in quiet transformation. The Industrial Revolution had reached Denmark's shores, bringing with it the hum of machines and the spirit of progress. Yet, in contrast to the mechanical rhythm of modernity, there remained a strong humanistic culture, a belief that science and philosophy were two sides of the same coin. This balance between rational thought and existential inquiry would later shape the essence of Bohr's scientific philosophy. From an early age, Niels understood that science was not only about equations, it was about interpretation, about meaning, about the dialogue between nature and the human mind. At Gammelholm Latin School, where he studied in his early years, Bohr displayed a deep interest in mathematics and physics. His teachers quickly recognized his extraordinary analytical ability. But Niels was not a student who simply memorized formulas. He questioned everything. He wanted to know why the world behaved as it did, why things moved, why light shimmered, why matter existed in the form it did. He approached learning not as an obligation, but as a journey. His notebooks were filled not only with calculations, but with reflections. His mind always weaving logic with curiosity. By the time Bohr entered the University of Copenhagen in 1903, his scientific temperament had begun to crystallize. He studied physics under Christian Christiansen, one of Denmark's leading physicists, and immersed himself in experimental and theoretical research. In those early years, physics itself was on the verge of revolution. The classical laws of Newton still reigned supreme, but new discoveries, radioactivity, the electron, and the mysterious energy quanta proposed by Max Planck, had begun to challenge the traditional order of things. Bohr found himself drawn to this frontier of uncertainty, where the old rules were breaking and the new ones were yet to be written. As a student, Niels Bohr was methodical but imaginative. His experiments were never mechanical repetitions, they were acts of interpretation. One of his early research projects, which would later become the foundation for his doctoral thesis, dealt with the properties of surface tension in liquids. It may sound like a modest topic, but Bohr's approach to it revealed the depth of his thinking. He wasn't just trying to measure surface tension. He was trying to understand the underlying laws governing it. He spent countless hours in the laboratory, building his own equipment, fine-tuning every detail, ensuring that his results were not just accurate but meaningful. His meticulous nature bordered on obsession, but it was this precision that defined his character. In those long hours of quiet experimentation, Bohr developed not only scientific skill but philosophical patience. He learned that nature does not reveal its secrets easily. One must listen to it, question it, and sometimes even doubt it. This relationship with uncertainty, which he cultivated as a young man, would later become the core of his quantum philosophy. Even then, Bohr began to realize that every answer in science opened the door to deeper questions, that the essence of discovery lay not in certainty, but in exploration. Outside the lab, Bohr's interests extended beyond physics. He read philosophy and literature, engaged in discussions on ethics, and pondered the relationship between science and society. The influence of his father's humanistic outlook remained strong within him. He often said that science was a way of thinking about life, a method of seeking truth that went beyond formulas. To Bohr, the search for understanding was a moral pursuit, not merely an intellectual one. He viewed knowledge as something that must serve humanity, not dominate it. The University of Copenhagen during Bohr's time was small but intellectually vibrant. The young physicist was surrounded by professors and peers who were intrigued by the emerging mysteries of atomic science. Yet Denmark, at that time, was far from the epicenters of modern physics like Berlin or Cambridge. For Bohr, this isolation was not a limitation. It was an opportunity. It allowed him to think independently, free from the constraints of rigid academic traditions. His ideas developed quietly, nurtured by his deep sense of wonder rather than by competition or recognition. In 1907, Bohr's father passed away suddenly. The loss was devastating. Christian Bohr had been more than a father. He had been a mentor, a source of inspiration, the embodiment of intellectual honesty and curiosity. For Niels, this tragedy deepened his introspection. He began to see science not only as a pursuit of knowledge, but as a tribute to his father's spirit, a continuation of the search for truth that his father had instilled in him. The emotional depth of this loss would later be reflected in the sensitivity and humility with which Bohr approached all scientific questions. As he progressed in his studies, Bohr's talent became undeniable. His doctoral thesis on the electron theory of metals, submitted in 1911, was a masterpiece of originality. While most physicists of the time were content with classical explanations, Bohr sought to address the inconsistencies that others ignored. He identified flaws in existing theories and proposed new interpretations that would later foreshadow the principles of quantum theory. His examiners, impressed by his insight, realized they were witnessing the emergence of a mind destined to transform physics. But what truly set Bohr apart was not only his intelligence, it was his humility. He never presented his ideas with arrogance. Instead, he spoke softly, thoughtfully, as if in dialogue with nature itself. He often paused before answering questions, not because he didn't know the answer, but because he wanted to ensure he understood the question deeply. This reflective quality became his trademark throughout his career. To those who met him, Bohr seemed less like a scientist and more like a philosopher, one who sought meaning as much as truth. During his years as a young researcher, Bohr's curiosity often took him beyond the walls of the laboratory. He would walk through the streets of Copenhagen, observing the world with quiet fascination. He saw science not as separate from life, but as an extension of it. He once remarked to a colleague that every great and deep difficulty bears in itself its own solution. This belief in the unity of problems and answers, in the harmony of contradictions, would later form the philosophical basis of his principle of complementarity. Even in his early 20s, Bohr sensed that the universe was not built upon absolutes but upon relationships, between light and matter, between observation and reality, between knowledge and mystery. By 1911, after completing his PhD, Bohr began his postdoctoral journey abroad. His first destination was the University of Cambridge, where he worked under the legendary J.J. Thomson, the discoverer of the electron. Yet, this experience was not as fruitful as he had hoped. Thomson, steeped in classical thinking, was not receptive to Bohr's unconventional ideas. The young physicist found himself constrained, unable to explore freely. But rather than becoming discouraged, Bohr took this as a lesson. He realized that the path to discovery often demands independence, that sometimes one must walk away from established authority to find truth. Shortly thereafter, Bohr moved to the University of Manchester to work under Ernest Rutherford, whose discovery of the atomic nucleus had recently shocked the scientific world. It was here, in the bustling laboratories of Manchester, that Bohr's earlier curiosity began to find direction. Rutherford's experiments had shown that atoms were mostly empty space, with a dense nucleus at the center. But the structure of the atom, the behavior of its electrons, remained a mystery. Bohr's mind immediately turned to this question. The curiosity that had driven him as a child now found its greatest challenge: to understand the invisible architecture of the atom itself. This moment marked the beginning of Bohr's transformation from a student of physics to one of its defining figures. Every lesson from his childhood, his father's guidance, his philosophical reflections, his patient experimentation, seemed to converge into a single purpose. He would not merely study the atom, he would reveal its secrets. Through those early years, Bohr's life reflected the evolution of modern science itself, a journey from certainty to mystery, from simplicity to depth. He had grown up in a world where physics explained the mechanical workings of the universe with confidence and precision. Yet he now stood at the edge of a new reality, one that defied intuition, one that demanded a new way of thinking. His curiosity, once sparked by the simple beauty of nature, was about to ignite a revolution that would change the way humanity understood existence. In this quiet evolution of thought, we see the essence of Niels Bohr's genius, not in sudden brilliance, but in his lifelong conversation with nature. His early years were not marked by fame or recognition, but by the steady growth of insight. It was the kind of mind that did not seek to conquer the mysteries of the world, but to coexist with them, to learn their language and listen to their silence. In every experiment, in every question, in every pause, Niels Bohr was preparing himself for the monumental discovery that awaited him. The child who once marveled at the ripples in a pond would soon uncover the ripples of reality itself, the quantum waves that define the fabric of the universe. The air in Manchester was thick with the scent of progress, the hum of machines, and the energy of discovery. In those dimly lit laboratories, Niels Bohr found the fertile ground his mind had long been searching for. Under the mentorship of Ernest Rutherford, he entered a world where theory met experiment in a delicate dance of precision and imagination. Rutherford's model of the atom, a tiny, dense nucleus surrounded by orbiting electrons, had opened the door to a new era in physics. Yet, for Bohr, something essential was missing. The model explained the atom's structure but not its stability. Why didn't the electrons, as classical physics predicted, spiral into the nucleus and collapse the atom? That question began to burn inside him like a quiet flame. Bohr spent long nights in thought, his desk illuminated only by a small lamp, papers scattered across the table, equations flowing like poetry. He was not merely solving a problem, he was seeking meaning in the mystery. Every calculation carried with it a philosophical question: how does nature sustain order amid chaos? How does stability arise from motion? The more he thought, the more he sensed that classical physics, the physics of Newton and Maxwell, was insufficient to describe the hidden order of the atom. Something deeper, more abstract, governed the subatomic world, something that defied the rigid logic of the macroscopic universe. During this time, the young physicist also found himself drawn to the revolutionary ideas of Max Planck and Albert Einstein. Planck's concept of energy quanta, tiny, discrete packets of energy, had already shaken the foundations of classical theory. Einstein had extended that idea to explain the photoelectric effect, showing that light itself behaved both as a wave and as a particle. To Bohr, these discoveries were more than mathematical curiosities. They were hints of a new reality, a new logic that operated beneath the surface of perception. He sensed that the atom's mystery could only be unlocked by embracing this dual nature of light and matter. But Bohr's journey was not without struggle. The scientific community was deeply rooted in the comfort of classical reasoning. The notion that energy could exist in quantized form, that nature might be discontinuous, was unsettling. Many of his peers saw it as absurd, even heretical. Yet Bohr's nature was not combative, he was patient, reflective. He did not seek to overthrow the old order violently, but to build a bridge between the old and the new. He often said that truth emerges not by destroying what came before, but by transcending it. That quiet belief guided his work and defined his legacy. In 1912, after a productive stay in Manchester, Bohr returned to Copenhagen, newly married to Margrethe N. A. Rolund, who would become his lifelong companion and emotional anchor. Their marriage was a partnership built on mutual respect and understanding. Margrethe's calm presence and sharp intellect provided Bohr with the emotional balance he needed to navigate the turbulent world of scientific thought. She would later play an important role in editing and clarifying his often complex writings, translating his deep, abstract ideas into words that others could grasp. Together, they built not only a family but also a haven of intellectual serenity, a place where ideas could breathe. In the years that followed, Bohr began developing his own vision of the atom. Drawing upon Rutherford's nuclear model and Planck's quantum hypothesis, he proposed something entirely new: that electrons do not orbit the nucleus in arbitrary paths, but in discrete, quantized orbits. When an electron jumps from one orbit to another, it emits or absorbs a photon corresponding to the difference in energy between those orbits. It was a daring idea, an elegant fusion of classical mechanics and quantum theory. The simplicity of the model concealed its profound implications. It explained the spectral lines of hydrogen, the mysterious fingerprints of light that had puzzled scientists for decades. When Bohr published his theory in 1913, it was met with astonishment. The scientific world had never seen such a synthesis of imagination and precision. Some called it visionary, others controversial. But within a short time, the Bohr model of the atom became a cornerstone of modern physics. It was the first step toward a deeper understanding of quantum structure, and though later refined and surpassed by quantum mechanics, its philosophical spirit continues to echo in every classroom and laboratory to this day. Yet, behind this monumental achievement was the same quiet curiosity that had guided Bohr since childhood. He never regarded his discovery as a triumph over nature, but as a dialogue with it. He believed that science was not about conquering truth, but about approaching it, slowly, humbly, and with wonder. His model of the atom was not just a scientific statement, it was a philosophical reflection of how he saw reality, as a balance between the known and the unknowable, between stability and motion, between logic and mystery. Bohr's curiosity was not limited to the atom, it extended to the nature of knowledge itself. He began to see patterns in the way human understanding evolves, how each generation builds upon the doubts of the previous one. To him, uncertainty was not a flaw in science, but a fundamental feature of it. Every answer contained within it a new question, and every discovery deepened the mystery rather than eliminating it. This view would later become the cornerstone of his interpretation of quantum mechanics, the Copenhagen Interpretation, which argued that reality itself cannot be separated from the act of observation. But even before formulating these ideas, Bohr's early life reflected this philosophy in action: his endless questioning, his patient observation, his refusal to settle for easy answers. The world around Bohr was also changing rapidly. The First World War had cast its shadow across Europe, disrupting communication and collaboration among scientists. But even in those uncertain times, Bohr remained dedicated to his work. His laboratory in Copenhagen became a small island of intellectual light amid the darkness of war. After the conflict ended, Bohr envisioned something greater, a place where physicists from all over the world could gather, free from political and cultural boundaries, united by the shared pursuit of knowledge. That vision would later give birth to the Institute for Theoretical Physics in Copenhagen, a sanctuary for the finest minds of the new quantum age. Bohr's early experiences shaped not only his scientific thinking, but his moral and philosophical outlook as well. He had grown up in a family that valued empathy and intellectual honesty. His father's belief that science must serve humanity left a lasting imprint on him. Throughout his life, Bohr carried that same conviction, that the power of knowledge must be guided by wisdom. He once said that every valuable human being must be a radical and a rebel, not in the sense of defiance for its own sake, but in the willingness to question accepted truths. For him, rebellion was a form of responsibility, the duty to seek deeper understanding, even when it challenges comfort. Those who knew Bohr during his early years often described him as serene yet intense, a man who listened more than he spoke. He had a way of turning silence into a form of communication. When he did speak, his words carried a strange blend of precision and poetry. He would pause mid-sentence, as if weighing the universe in his thoughts before choosing the right word. His students often recalled that his pauses were more profound than most people's lectures. This contemplative style was not an affectation. It was the reflection of a mind that truly listened, both to others and to nature itself. As Bohr's reputation grew, so did the philosophical depth of his reflections. He began to see parallels between the contradictions in human nature and those in physical theory. Just as the atom contained opposites, stability and energy, motion and stillness, so too did the human spirit. Bohr's idea of complementarity, which would later define his philosophical approach, was born from this insight that reality is not a matter of either or, but both, and light could be both wave and particle, truth could be both rational and paradoxical. This way of thinking traced its roots back to the same curiosity that had once made him stare at ripples in a pond, wondering how two seemingly opposite waves could merge into harmony. By the 1920s, Bohr's name had become synonymous with the birth of quantum physics. Yet he never lost the humility of that young boy from Copenhagen. When asked about his achievements, he often deflected praise, emphasizing the collective nature of discovery. He saw science as a human endeavor, a conversation across generations where each scientist added a small piece to an ever-growing mosaic of understanding. This humility stemmed not only from his character but from his worldview. To Bohr, the universe itself was humble in its grandeur. It revealed just enough to inspire wonder, yet always withheld the final answer. As he mentored a new generation of scientists, among them Werner Heisenberg, Wolfgang Pauli, and many others, Bohr encouraged them to embrace uncertainty rather than fear it. He reminded them that confusion was not failure. It was the beginning of insight. His students would later recall how he treated every question with equal seriousness, whether it came from a young student or a fellow Nobel laureate. For Bohr, knowledge was not a hierarchy but a dialogue. His early upbringing in a family that valued open discussion had become the foundation of his scientific leadership. Even in his personal life, Bohr's curiosity never waned. He was fascinated by language, culture, and art, often drawing analogies between science and creativity. He once told a colleague that science and art were two ways of expressing the same truth, one through logic, the other through emotion. To him, the beauty of a scientific theory lay in its simplicity, its harmony with nature, much like the beauty of a poem or a painting. This aesthetic sensibility made his scientific work not just rational, but deeply human. Looking back at Bohr's early life, one can see how every experience, his childhood curiosity, his father's influence, his patient experiments, his philosophical reflections, converged into the making of a scientific mind unlike any other. His journey from the quiet streets of Copenhagen to the heart of the atomic mystery was not a sudden ascent, but a steady unfolding, guided by the belief that understanding begins with wonder. He had inherited from his father the courage to question, from his mother the sensitivity to listen, and from his own heart the determination to seek truth without fear of uncertainty. When the world later celebrated Niels Bohr as the father of quantum theory, few could have imagined that his greatness had been forged not in moments of triumph, but in years of quiet contemplation. The young man who once built homemade experiments in his father's lab had grown into the philosopher of the atom, the man who turned doubt into a principle of knowledge. His early life stands as a testament to the power of curiosity, the kind of curiosity that does not fade with answers, but deepens with them. In the end, Niels Bohr's legacy is not only found in his equations or theories, but in the way he approached the unknown. His early life was a mirror of the scientific spirit itself, the courage to ask, the patience to wait, the humility to learn, and the faith to believe that even in the deepest mysteries, meaning can be found. The story of his youth is not just the beginning of a scientist's journey. It is the birth of a way of seeing the universe, where curiosity becomes the bridge between the human mind and the infinite complexity of nature. Through that lifelong conversation with the cosmos, Bohr became more than a physicist. He became a symbol of intellectual integrity, a reminder that the quest for knowledge begins in the simple wonder of a child looking at the world and asking, quietly but endlessly, why? At the dawn of the 20th century, science stood at a crossroads. The world had begun to peer into the heart of matter, yet the structure of the atom remained one of its most perplexing mysteries. The atom, once thought to be indivisible, had been revealed to contain smaller, more fundamental components: electrons, protons, and the mysterious nucleus discovered by Ernest Rutherford. But how these parts were arranged, and how they interacted, puzzled even the greatest minds. The classical laws of Newton and Maxwell could not explain the strange behavior observed in atomic phenomena. It was as though nature had placed a veil between the visible world of everyday objects and the invisible realm of atomic existence. And into that darkness stepped a quiet, thoughtful man from Copenhagen, Niels Bohr, armed not with power but with imagination. When Bohr arrived at Rutherford's laboratory in Manchester in 1912, he entered an atmosphere of excitement and confusion. Rutherford had recently proposed his planetary model of the atom, a dense, positively charged nucleus surrounded by orbiting electrons. It was a bold idea, but it carried within it a fatal flaw. According to classical physics, electrons moving in circular orbits around a nucleus should continuously emit electromagnetic radiation. This loss of energy would cause them to spiral inward and collapse into the nucleus within a fraction of a second. Yet, clearly, atoms were stable. Matter did not simply vanish into energy. Something in the classical picture was wrong, fundamentally wrong. Bohr sensed that the solution would require more than mathematical correction. It would demand a new way of thinking about reality itself. In the quiet hours of evening, Bohr would sit by his desk, surrounded by books, equations, and fragments of thought. He revisited the works of Planck and Einstein, those early pioneers who had dared to question the continuous nature of energy. Planck had proposed that energy was emitted or absorbed in discrete packets called quanta, each proportional to the frequency of radiation. Einstein had extended that concept, suggesting that light itself could behave as particles, photons. What if, Bohr wondered, the same quantum idea could be applied not just to light, but to the atom itself? What if the motion of electrons around the nucleus was not continuous but quantized? It was a daring thought, so audacious that few of his contemporaries would have even entertained it. But Bohr's mind worked differently. He did not fear paradoxes, he sought harmony within them. He imagined the atom not as a miniature solar system obeying Newton's laws, but as a dynamic, self-consistent system governed by new rules, rules that might appear strange, even illogical, yet reflected the hidden rhythm of nature. As days turned into nights, Bohr refined his vision. He proposed that electrons could orbit the nucleus only in specific, stable paths or energy levels. As long as an electron remained in one of these allowed orbits, it would not emit radiation, defying the expectations of classical electromagnetism. Only when an electron jumped from one orbit to another would it emit or absorb energy in the form of a photon, equal to the difference between the two energy levels. This simple yet profound idea connected the microscopic architecture of the atom with the mysterious spectra of light observed in laboratories across the world. For decades, scientists had puzzled over the bright and dark lines in the spectrum of hydrogen, each line corresponding to a specific wavelength of light emitted or absorbed by the atom. Classical theory could not explain why only certain wavelengths appeared, why the spectrum was not continuous. Bohr's model provided the missing key. His quantized orbits gave rise to discrete energy transitions that perfectly matched the observed spectral lines. For the first time, theory and experiment aligned in beautiful harmony. It was as if the universe had finally whispered one of its secrets, and Bohr had been there to listen. When his paper on the constitution of atoms and molecules was published in 1913, it sent ripples through the scientific community. The simplicity of Bohr's model belied its revolutionary implications. It suggested that the universe, at its most fundamental level, was not continuous but discrete, that nature moved not in smooth curves but in quantum leaps. The familiar, deterministic world of classical mechanics gave way to a probabilistic realm where certainty was replaced by possibility. Bohr's atom became the first window into this new landscape. Yet, Bohr himself was not intoxicated by fame or triumph. He understood that his model was not the final truth, but a step forward, a bridge between the old physics and the new. He was acutely aware of its limitations. His theory worked remarkably well for hydrogen, but failed to fully describe more complex atoms. Nevertheless, the conceptual leap it represented could not be overstated. It redefined not only atomic theory, but the very philosophy of science. For the first time, physicists began to see that laws governing the microscopic world might differ fundamentally from those governing the macroscopic one. The age of classical certainty was over. In those years, Bohr's mind seemed to radiate quiet intensity. He was still a young man, only in his late 20s, yet his vision had already begun to reshape physics. He corresponded with the greatest scientific minds of his time, Einstein, Planck, Sommerfeld, engaging in deep discussions about the meaning of his theory. Many admired his courage, others remained skeptical. Einstein, while impressed by Bohr's brilliance, was uneasy about the introduction of discontinuity into physics. The very idea that electrons could jump from one orbit to another without existing in between defied common sense. But Bohr's response was characteristically calm. Nature, he believed, was not obliged to conform to human intuition. Meanwhile, his model inspired a generation of young physicists eager to explore the new quantum frontier. Arnold Sommerfeld extended Bohr's theory to include elliptical orbits, explaining the fine structure of spectral lines. Others built upon his ideas, refining, expanding, and questioning them. The atomic model became a living concept, evolving with each new discovery. But Bohr remained its philosophical heart, the quiet center around which the chaos of innovation revolved. Beyond the laboratory, Bohr's model had a profound cultural impact. It marked a turning point not just in science, but in human thought. The atom had long been a symbol of stability, the indivisible building block of matter. Now, Bohr revealed it to be a dynamic, almost living entity, a system of motion, energy, and change. The atom was no longer a static point, it was a miniature universe of probabilities and transformations. This vision captured the imagination of artists, philosophers, and writers alike. The early 20th century, with its revolutions in art, literature, and psychology, found in quantum theory a mirror of its own restless search for meaning. Bohr's contribution went beyond the technical. His model embodied a philosophical shift, the recognition that knowledge has limits, that observation and reality are intertwined. In creating his atomic model, he had not only solved a scientific puzzle, but introduced a new way of thinking about the relationship between theory and experience. His insistence on connecting abstract equations with physical meaning distinguished him from many of his contemporaries. He believed that scientific theories must describe phenomena, not just predict them. To Bohr, physics was not merely a tool for calculation, it was a language for understanding nature's conversation with itself. As his fame grew, Bohr remained remarkably grounded. In 1916, he accepted a professorship at the University of Copenhagen, where he began to gather a group of brilliant young minds. His lectures were unlike any other. He spoke slowly, often pausing mid-sentence, searching for the precise word that could capture the delicate balance between logic and mystery. His students sometimes found these pauses frustrating, but they soon realized that those silences contained more meaning than many words. Bohr was not teaching them answers, he was teaching them how to think. The impact of Bohr's atomic model also extended into experimental physics. It provided a theoretical framework that guided countless experiments in spectroscopy, X-ray analysis, and chemical bonding. Scientists could now predict and interpret the behavior of atoms with unprecedented accuracy. The periodic table, once an empirical arrangement of elements, found a new foundation in Bohr's quantum structure. Each element's chemical properties could be explained by the arrangement of electrons in its quantized orbits. Chemistry and physics, once separate disciplines, began to merge into a unified vision of matter. But perhaps the most profound aspect of Bohr's achievement was its philosophical depth. In proposing his model, Bohr had unwittingly introduced the principle of complementarity, the idea that seemingly contradictory descriptions of nature could both be true, depending on the context. The electron could behave as both a particle and a wave, light could be both continuous and discrete. These paradoxes, rather than being signs of failure, were clues to a deeper harmony underlying reality. This insight would later form the core of Bohr's interpretation of quantum mechanics, but its roots lay in his early atomic theory. The Bohr model was more than a scientific hypothesis, it was a window into the dual nature of existence itself. The world, still reeling from the devastation of World War I, found in Bohr's work a glimpse of order amid chaos. His atom was not a symbol of destruction but of unity, a reminder that even the smallest components of nature follow laws of balance and proportion. In an age when nations had torn each other apart, Bohr's vision of the atom as a harmonious system resonated deeply. It suggested that beneath the turbulence of events, there existed a deeper coherence, a quiet rhythm that held the universe together. As Bohr continued his research, he remained deeply aware of the fragility of understanding. He knew that his model was only a beginning, a stepping stone toward a more complete theory, but that humility was his strength. He once remarked that, "Every valuable idea seems impossible at first." To him, science was a journey without end, a process of constant refinement and self-correction. His atomic model would soon give way to more advanced quantum mechanics, developed by Heisenberg, Schrödinger, and Dirac, yet its spirit, the fusion of intuition, imagination, and precision, would continue to define the field. For Bohr, the true impact of his atomic theory was not measured in fame or accolades, but in the questions it inspired. It had opened a door to a new realm of thought, where certainty was replaced by probability, where reality itself seemed to depend on observation. This new understanding of nature would challenge not only physics but philosophy, psychology, and even theology. It redefined humanity's place in the cosmos, not as detached observers, but as participants in the unfolding mystery of existence. In those transformative years, Bohr often returned in thought to his childhood, to the quiet curiosity that had driven him to ask why the world behaved as it did. Now, as the architect of a new vision of matter, he saw the same curiosity reflected in the faces of his students, in the pages of scientific journals, in the restless debates of his peers. He had not merely solved a problem, he had ignited a movement, a revolution of thought that would reshape the century. The Bohr model was, at its heart, an act of imagination, the leap from what could be seen to what must be true. It taught humanity that the universe, though complex, could be understood if approached with humility and creativity. It was a reminder that science, like art, begins with wonder, and that every discovery is a conversation between mind and nature. Through his vision, Niels Bohr transformed the atom from a mystery into a masterpiece, a universe within a universe, governed by rules as subtle as they are profound. In the following years, Niels Bohr's model of the atom evolved from a bold hypothesis into one of the most transformative breakthroughs in modern physics. The second half of his journey into atomic understanding revealed the depth of his intellect and the persistence of his curiosity. Bohr was not content with theoretical triumph alone. He wanted to refine, test, and expand the model to ensure that it aligned with the unfolding discoveries of his time. As he continued to explore the mysterious world of subatomic particles, Bohr's influence spread rapidly through the global scientific community. His atomic theory became a framework that not only redefined the atom, but also laid the foundation for quantum mechanics, a theory that would forever alter humanity's grasp of nature's deepest laws. After publishing his model in 1913, Bohr began receiving recognition and equally criticism from fellow scientists. Many admired his courage in combining the classical mechanics of Newton with the new quantum ideas of Max Planck. Yet others questioned whether his concept of discrete orbits truly reflected physical reality or was merely a convenient mathematical construction. Bohr welcomed these challenges, for he believed that science thrived on uncertainty and open debate. His Copenhagen office became a hub for discussions that blurred the line between philosophy and physics. There, he and his colleagues would often spend long hours dissecting every aspect of atomic behavior, challenging each assumption until only the most refined truths remained. Over time, experimental results began to vindicate Bohr's model. The hydrogen spectrum, which displayed distinct lines when light passed through a prism, fit perfectly with his predicted energy levels. This success gave his theory remarkable credibility, as it not only explained what was already known but also predicted new phenomena that would later be confirmed. The atomic world, once a realm of speculation, now had a measurable structure, one governed by precise yet mysterious rules of energy transitions. Bohr's atom was not static but dynamic, filled with motion and transformation. Every jump of an electron represented a quantum leap, a moment of energy exchange that defined the invisible processes shaping the universe. As his fame grew, Bohr became a mentor to a new generation of physicists who flocked to Copenhagen from around the world. His institute became a sanctuary for those seeking to explore the new frontiers of matter and energy. Young minds such as Werner Heisenberg, Wolfgang, and Paul Dirac found in Bohr not only a teacher but a guide, a thinker who balanced deep mathematical understanding with profound philosophical reflection. Under his mentorship, the boundaries of physics expanded beyond traditional mechanics and ventured into the uncertain, probabilistic world of quantum behavior. In this creative environment, the Bohr model evolved. It was no longer viewed as a complete description of the atom, but as a vital step toward a deeper truth. Bohr himself recognized its limitations. His model worked beautifully for hydrogen, but struggled with more complex atoms. He encouraged others to go beyond his framework, to challenge his assumptions and seek a more comprehensive quantum theory. It was this intellectual humility that defined Bohr's greatness. He understood that science was not about final answers, but about the pursuit of better questions. His focus then turned toward integrating the wave-like behavior of electrons, a concept introduced by Louis de Broglie, into atomic theory. This shift paved the way for quantum mechanics as formulated by Schrödinger and Heisenberg. Although Bohr's model would eventually be replaced by these more advanced theories, his influence remained fundamental. It was Bohr who first proposed that the atom's stability and spectral properties could only be explained by quantized energy levels. Every later advancement built upon this core principle. Beyond the scientific details, Bohr's model symbolized a new way of seeing the universe. It broke away from the deterministic worldview of classical physics and embraced a layered reality, one where energy and matter behaved both as particles and waves, where observation affected outcomes, and where uncertainty was not chaos, but a reflection of deeper order. This philosophical shift echoed through the entire scientific world, influencing not only physicists, but also philosophers and artists who were fascinated by the blurred boundaries between certainty and mystery. Bohr's atomic theory also carried profound implications for humanity's technological progress. From the development of spectroscopy to the birth of quantum electronics, the principles he introduced became the foundation of modern science and engineering. The very technologies that power our age, lasers, semiconductors, and quantum computers, trace their lineage to Bohr's vision of quantized energy transitions. His model did more than explain the atom, it unlocked the possibility of controlling and harnessing the forces within it. Even as his scientific achievements multiplied, Bohr remained deeply reflective about their meaning. He often spoke about the relationship between knowledge and understanding, insisting that every discovery came with both clarity and confusion. To him, the atom was not just a physical entity, but a metaphor for the complexity of existence. It was a symbol of balance between order and unpredictability, a reminder that every leap in knowledge requires an acceptance of mystery. Bohr's famous phrase, "The opposite of a correct statement is a false statement, but the opposite of a profound truth may well be another profound truth," captured the essence of his worldview. He saw contradictions not as obstacles, but as paths toward deeper understanding. As the years passed, Bohr's reputation as one of the greatest thinkers of his generation solidified. He received the Nobel Prize in Physics in 1922 for his work on the structure of atoms and the emission of radiation. Yet even with global acclaim, Bohr remained modest and approachable. Those who visited him often described his conversations as enlightening, but also challenging, filled with long pauses and thoughtful silences. He encouraged his students to think critically, to embrace doubt as a necessary step toward discovery. In the later stages of his life, Bohr's atomic model became a historical cornerstone, a starting point from which quantum theory took flight. The simplicity of his vision, an electron orbiting a nucleus in quantized steps, continued to inspire not because it was complete, but because it revealed the power of imagination in science. It showed that even the smallest leap in understanding could reshape the universe. Bohr's work demonstrated that true genius lies not in constructing perfect theories, but in asking the right questions. His atomic model was never just about the atom. It was about the nature of reality itself, about the boundaries of human perception, and the courage to explore beyond them. It invited the world to see that beneath every solid surface lies a sea of uncertainty, and within that uncertainty, the blueprint of creation. In essence, Niels Bohr's atomic theory marked the birth of a new era. It united physics with philosophy, knowledge with wonder, and science with imagination. It was a journey from the visible to the invisible, from simplicity to complexity, from certainty to possibility. And even today, when modern physics has ventured far beyond the limits of Bohr's original model, the spirit of his discovery lives on. Every time we split an atom, observe a quantum jump, or manipulate a photon, we echo Bohr's vision, a vision that forever changed how we see the universe and our place within it. Niels Bohr's model did more than define an atom, it defined a way of thinking, a balance between logic and imagination, precision and philosophy. It opened the door to the quantum age and laid the first stones of a path that science continues to walk. The atom, once thought indivisible, became a symbol of infinite depth, and through Bohr's insight, humanity took its first real glimpse into the fabric of reality itself. At the turning point of the 20th century, physics was standing on the edge of revolution. The old world of classical mechanics, built by Newton and perfected by Maxwell, was beginning to show cracks under the weight of new discoveries. The laws that had once explained the motion of planets and the fall of apples could no longer describe the strange, invisible behavior of the atomic world. In this period of confusion and curiosity, one mind began to weave the threads of a new understanding, Niels Bohr. His thoughts, bold and transformative, gave birth to the language of the quantum world. The birth of quantum theory was not a single discovery, but a gradual awakening, and at its heart was Bohr's vision. A vision that turned uncertainty into knowledge, probability into law, and mystery into meaning. By the early 1900s, physicists knew that matter was made of atoms, but what happened inside these atoms remained a puzzle. Experiments, such as those by Ernest Rutherford, had shown that most of the atom's mass lay in a tiny, positively charged nucleus surrounded by electrons. Yet classical physics could not explain how these electrons behaved. According to old laws, electrons moving in circular orbits should lose energy continuously, spiraling into the nucleus within a fraction of a second. Yet matter was stable. Something was missing, something deeper than anyone had imagined. Bohr entered this landscape of confusion with a daring proposal. In 1913, he introduced the idea that electrons do not move freely in any orbit, but instead occupy fixed energy levels. These orbits were quantized, meaning electrons could only exist in specific states and could jump between them by absorbing or releasing energy in discrete packets called quanta. It was a radical idea, one that broke the continuous flow of classical physics and replaced it with a world of sudden leaps and invisible transitions. This concept was not just a refinement of earlier models, it was a complete shift in how reality was understood. Bohr's model explained the spectral lines of hydrogen with mathematical precision, giving the first evidence that the atom was governed by quantum rules. But the importance of Bohr's insight went far beyond hydrogen. It suggested a new framework for all physical processes. The universe was no longer a mechanical clock ticking predictably, it was a dance of probabilities, a symphony of energy exchanges occurring at the smallest scales. Bohr's work inspired other physicists to push these ideas further. Planck's quantum hypothesis, Einstein's photon theory, and Bohr's atomic model together laid the foundation of what would soon become quantum theory, a new branch of physics that would redefine the limits of human understanding. Bohr's quantum vision was not merely scientific, it was deeply philosophical. He saw that at the atomic level, nature did not behave according to the simple logic of everyday experience. Instead, it followed principles that defied intuition. He realized that to understand the atom, one had to let go of classical certainty. The behavior of electrons could not be described by definite paths or trajectories, but only by probabilities, chances of being here or there, of acting this way or that. The observer could no longer stand outside the experiment, observation itself became part of the event. This idea would later evolve into the famous principle of complementarity, the notion that particles and waves, certainty and uncertainty, all coexist as aspects of a deeper truth. As Bohr continued his research, he found himself at the center of an emerging intellectual movement that stretched across Europe. The early pioneers of quantum physics, Heisenberg, Schrödinger, Pauli, Dirac, all contributed their ideas to this evolving picture of the micro-world. Bohr's influence guided much of this progress. His Copenhagen Institute became the headquarters of a new kind of physics, one where discussion, doubt, and debate were as important as equations. Young physicists came from every corner of the world to learn from him, drawn not only by his brilliance, but by his humility and openness. Bohr's office was a space of free thought, where every question was welcome and no idea was too wild to explore. The emergence of quantum theory under Bohr's guidance was more than the development of a new scientific theory. It was a philosophical revolution. It forced humanity to question the nature of knowledge itself. What does it mean to know something if the act of observation changes what we see? Can reality exist independently of our measurements? These questions, born from Bohr's work, transcended physics and entered the realms of metaphysics and philosophy. Bohr's ideas suggested that the universe was not a passive collection of objects, but an active interplay between observer and observed, energy and form, possibility and reality. Bohr's collaboration and sometimes opposition with Einstein played a key role in shaping quantum thought. Einstein respected Bohr but remained skeptical of the indeterminacy at the heart of quantum theory. God does not play dice with the universe, Einstein famously said. Bohr responded gently, but firmly, Einstein, stop telling God what to do. This exchange was more than a witty remark. It captured the essence of their philosophical divide. Einstein sought certainty, hidden variables that would restore determinism. Bohr accepted uncertainty as a fundamental feature of nature. For Bohr, probability was not ignorance of underlying truth, it was truth itself, the language of the atomic world. Throughout the 1920s, as quantum mechanics took its final shape, Bohr's presence remained guiding and unifying. When Heisenberg developed matrix mechanics and Schrödinger proposed wave mechanics, it was Bohr who helped interpret and reconcile these seemingly different pictures. He proposed that they were not contradictory, but complementary views of the same phenomenon, two languages describing the same underlying reality. This insight, known as Bohr's principle of complementarity, became one of the philosophical cornerstones of quantum theory. The development of quantum theory marked one of the greatest intellectual achievements in human history, and Bohr stood at its center. His model of the atom had provided the first glimpse into a quantized world, and his philosophical insights gave meaning to the equations that followed. He transformed quantum mechanics from a mathematical puzzle into a coherent vision of reality, a reality that was dynamic, interconnected, and alive with possibilities. As Bohr's influence spread, so did the practical consequences of his ideas. The understanding of atomic energy led to technological advances that reshaped the 20th century, from nuclear physics to electronics and quantum chemistry. Yet Bohr remained cautious about the power of science. He believed that with great knowledge came great responsibility. During World War II, he became an advocate for international cooperation in scientific research, warning against the destructive potential of atomic energy. His vision of science was deeply moral, a pursuit not just of knowledge but of wisdom. By the 1930s, Bohr's contributions had become legendary. He was no longer just a physicist, he was a thinker who shaped how humanity perceived existence itself. To Bohr, the quantum world revealed that reality is not fixed but fluid, that observation creates participation, and that truth can take multiple forms without contradiction. These ideas were revolutionary not only in science, but also in how people thought about life, consciousness, and the universe. Even decades after his discoveries, Bohr's concepts remain at the heart of physics. Quantum theory governs everything from the behavior of electrons in atoms to the functioning of stars, from the logic of computers to the mysteries of black holes. Every time a quantum computer processes information or a laser beam guides a surgical tool, Bohr's legacy lives on. His vision of the quantized atom was the first window into this new universe, a universe where energy comes in packets, matter behaves like waves, and reality itself dances between the possible and the actual. In the first half of this journey, from Bohr's atomic model to the full emergence of quantum theory, one truth stands out. It was not just the discovery of a new science, but the birth of a new way of thinking. Niels Bohr taught the world that the universe cannot be reduced to simple mechanisms, it must be understood as a tapestry of interwoven possibilities. His mind did not merely define quantum theory. It redefined what it means to understand. Bohr's work was not an end but a beginning, the opening act of a story that continues to unfold in every experiment, every particle, every spark of light that reveals the invisible heart of creation. As the foundations of quantum theory deepened, Niels Bohr found himself in the center of an intellectual storm unlike any other in the history of science. The atom was no longer a simple solar system in miniature. It had become a mysterious, pulsating realm of uncertainty and probability. In this strange new world, Bohr's ideas continued to evolve, shaping not only the equations that defined quantum behavior, but also the philosophy that sought to interpret it. The second half of his journey into the birth of quantum theory was not about discovery alone. It was about understanding what those discoveries truly meant. For Bohr, science was not merely a tool to measure nature. It was a mirror through which humanity glimpsed its own limitations and its power to perceive reality itself. By the mid-1920s, the basic structure of quantum theory was beginning to take shape. The mathematical frameworks of Heisenberg and Schrödinger provided powerful tools to describe atomic phenomena, but they left many physicists puzzled about what those equations actually meant. Could electrons really exist as waves of probability until observed? Could measurement itself determine reality? These were not simple questions of physics. They were questions that touched the core of existence. It was Bohr who took upon himself the monumental task of giving philosophical coherence to this new science. Through endless discussions with his students and colleagues in Copenhagen, he built what came to be known as the Copenhagen Interpretation, a view that would define quantum mechanics for generations. The Copenhagen Interpretation proposed that the act of observation plays a crucial role in the behavior of quantum systems. According to Bohr, a particle does not possess definite properties like position or momentum until it is measured. Until that moment, it exists in a superposition, a blend of possibilities. Only when observation occurs does one outcome become real. This was not an easy idea for the scientific mind to accept. It implied that reality at its most fundamental level was not objective but participatory. The observer and the observed were inseparable, woven together in a single act of measurement. Bohr's interpretation did not deny the existence of reality, rather it redefined it, suggesting that what we call real is always shaped by how we look at it. Einstein, who had helped create quantum theory with his work on light quanta, was deeply troubled by this interpretation. He could not accept a universe that relied on chance and observation. "Do you really think the moon isn't there when you're not looking at it?" he once asked. Bohr replied that quantum mechanics did not deal with such everyday objects, but with the subatomic world, where the rules of logic were different. Their debates stretched for decades, marked by mutual respect but profound disagreement. Bohr often responded to Einstein's criticisms with calm patience, emphasizing that quantum mechanics was not about what was, but about what can be known. To Bohr, the question of whether particles had definite properties when unobserved was meaningless. What mattered was what could be measured and described through experiment. This philosophical stance reshaped not only quantum mechanics, but also the nature of scientific inquiry itself. Bohr's approach replaced the rigid determinism of classical physics with a framework built on probability, complementarity, and contextuality. His principle of complementarity stated that wave and particle descriptions of matter were not contradictory, but complementary. Both were necessary to capture the full nature of quantum phenomena. This principle became one of the cornerstones of quantum theory, influencing every aspect of modern physics from atomic structure to quantum field theory. In Bohr's view, quantum mechanics revealed a universe that was inherently dual and interconnected. Light could behave as both a wave and a particle, depending on how one chose to observe it. Electrons could act as diffuse clouds of probability or as discrete points of energy. The very fabric of reality seemed to shift under the gaze of the observer, revealing that truth was not singular but layered. This was a revolutionary way of thinking, a departure from centuries of belief in fixed, objective reality. Bohr's universe was one of balance and paradox, where opposites did not cancel each other out but completed each other. The impact of these ideas spread far beyond physics. Philosophers, writers, and even artists began to draw inspiration from Bohr's interpretation of the quantum world. To many, his ideas symbolized the complexity of modern existence, the notion that truth could have multiple perspectives, that uncertainty was not ignorance but an intrinsic feature of life. In literature and art, the quantum revolution found expression in abstract forms and fragmented narratives that reflected the probabilistic nature of reality. Bohr himself, though humble and quiet, became a symbol of intellectual courage, a man who dared to question the very foundations of knowledge. As the years progressed, quantum theory evolved from philosophical debate into technological power. The understanding of quantum behavior gave rise to innovations that transformed the world: transistors, semiconductors, lasers, and ultimately, computers. Later in the 21st century, the very principles that Bohr and his contemporaries struggled to interpret became the basis for quantum computing and quantum communication. These technologies, capable of processing information at unimaginable speeds, stand as living proof of Bohr's enduring legacy. His abstract ideas about probabilities and measurements now underpin the devices that define modern civilization. Yet Bohr never lost sight of the human dimension of science. He often reminded his students that knowledge brought both enlightenment and responsibility. During the development of nuclear weapons in World War II, Bohr advocated for openness and international dialogue among scientists. He understood that the same quantum insights that explained the atom's behavior could also unleash destructive power. After the war, he worked tirelessly to promote peaceful uses of atomic energy and to encourage scientific collaboration across nations. His belief that science should serve humanity, not dominate it, reflected the depth of his moral vision. In the later years of his life, Bohr continued to refine his philosophical ideas. He believed that the lessons of quantum theory extended beyond physics, offering a model for understanding human thought and society. Just as particles could only be described in relation to how they were measured, so too could human ideas be understood only in the context of their interaction with others. This perspective of complementarity became, for Bohr, a universal principle, a way of seeing not just nature but the relationships between people, ideas, and cultures. Looking back, the birth of quantum theory stands as one of humanity's greatest intellectual milestones, and Niels Bohr's role in it remains central. He transformed chaos into clarity and paradox into principle. He showed that knowledge does not end with certainty, but begins with doubt. Through his work, the universe revealed itself as both mysterious and knowable, unpredictable yet harmonious. The quantum world that Bohr helped to define is not distant or abstract. It is the foundation of everything we see and touch, every atom in our bodies, every spark of light in the sky. Bohr's legacy endures not only in the laboratories of physics, but in the way we think about truth itself. His vision of reality, fluid, relational, and deeply interconnected, has influenced generations of scientists and thinkers. He taught that understanding requires humility, that truth is never absolute, and that mystery is not the enemy of knowledge but its companion. Through Niels Bohr, the birth of quantum theory became more than a scientific revolution. It became a new way of seeing the universe, one that continues to shape the human quest for meaning in a cosmos that is both infinite and intimately alive. In the midst of the quantum revolution, one of the most fascinating chapters of Niels Bohr's life unfolded through his intellectual encounters and collaborations with Albert Einstein. These two giants of physics, though united in their search for truth, stood on opposite sides of one of the most profound philosophical divides in science. Their debates over the nature of reality, certainty, and the limits of human knowledge were not mere academic disagreements. They were dialogues that shaped the very foundation of modern physics. The world watched as Bohr and Einstein, two of the sharpest minds in history, wrestled with questions that transcended mathematics and entered the realm of existence itself. Einstein, whose theory of relativity had redefined space and time, believed that the universe was governed by precise, deterministic laws. To him, every event had a cause, and randomness was only an illusion born of incomplete understanding. Bohr, on the other hand, stood as the guardian of quantum uncertainty. The idea that at the smallest scales of reality, Outcomes could not be predicted with certainty, only with probability. Where Einstein saw chaos as unacceptable, Bohr saw it as the essence of nature's truth. Their debates were more than scientific. They were philosophical battles about the meaning of knowledge and the boundaries of human reason. These legendary discussions began in the late 1920s, particularly during the Solvay conferences in Brussels, where the world's leading physicists gathered to debate the emerging quantum theory. Einstein often arrived with thought experiments designed to expose what he saw as flaws in the probabilistic nature of quantum mechanics. He famously declared, "God does not play dice with the universe," expressing his disbelief in a world ruled by chance. Bohr, calm and patient, responded that it was not humanity's place to tell nature how to behave. He argued that quantum theory did not describe hidden realities, but provided the most complete possible understanding of phenomena as they appeared to human observation. One of their most famous exchanges centered on the concept of measurement. Einstein proposed that one could determine both the position and momentum of a particle simultaneously with clever experimental setups, which would violate Heisenberg's uncertainty principle. Bohr meticulously analyzed each of Einstein's proposals and showed, through precise reasoning, that the uncertainty principle held firm. Every time Einstein tried to expose a loophole, Bohr closed it with insight and logic. Their debates were fierce but filled with mutual respect. Neither man sought victory for ego, but rather for truth. Through these exchanges, Bohr's philosophical depth shone brightly. He introduced the principle of complementarity, the idea that light and matter can display both wave-like and particle-like properties, but never both at the same time. The nature observed depends on the experiment performed. This principle became a cornerstone of quantum mechanics, bridging the gap between conflicting views and showing that reality could hold multiple, equally valid aspects that only appear contradictory when seen through a limited lens. Bohr's complementarity offered a new kind of logic, one that accepted duality as fundamental to nature's design. Einstein admired Bohr's intellect, but could never fully accept his conclusions. The two men remained in friendly opposition for decades, their debates continuing through letters and personal meetings. Einstein's skepticism inspired others, such as David Bohm, to search for hidden variables that might restore determinism to physics, but these efforts never replaced Bohr's interpretation as the dominant framework. Even as quantum mechanics became one of the most successful theories in science, predicting countless experimental results, Einstein continued to argue that it was incomplete. Bohr, however, maintained that completeness in science did not mean absolute certainty, but the best possible description of phenomena given the limits of observation. Their dialogue did not end in resolution, but in something greater, a shared acknowledgement of mystery. Bohr and Einstein's debates revealed that science is not a closed system of answers, but an evolving conversation between mind and nature. The tension between their ideas drove generations of physicists to explore the meaning of quantum reality, leading eventually to new interpretations and experimental tests that continue even today. Quantum entanglement, a concept Einstein once called spooky action at a distance, later became a cornerstone of modern physics and quantum information science. Further proof of how their debates shaped the future. In the end, the Bohr-Einstein debates were not about who was right or wrong, but about how humans seek truth in a universe that resists simplification. Bohr's calm acceptance of uncertainty and Einstein's demand for order represented two sides of the same pursuit, the balance between freedom and structure, chaos and law. Together, they showed that progress in science comes not from agreement, but from creative tension, from minds unafraid to question even the most fundamental beliefs. Niels Bohr's exchanges with Einstein revealed the depth of his vision. He did not see uncertainty as a flaw in understanding, but as a reflection of nature's subtlety. He believed that the universe was not made to conform to human logic, but to challenge it, to push consciousness toward greater awareness. Through his debates with Einstein, Bohr helped crystallize the philosophical heart of quantum mechanics, a recognition that reality is not fixed but fluid, shaped by observation and perspective. Their dialogue became a timeless symbol of intellectual courage, reminding the world that even disagreement, when pursued with respect and insight, can lead to the highest form of understanding. As the quantum revolution matured, Niels Bohr's influence extended far beyond the laboratory or lecture hall. He became not only a physicist but a philosopher of science and a guide for generations who sought to understand both the nature of the atom and the nature of truth itself. Bohr's legacy reached its peak through his role as a teacher, a mentor, and an architect of modern scientific thought. His institute in Copenhagen, known as the Niels Bohr Institute, became a sanctuary for some of the most brilliant minds of the 20th century. It was there that the foundations of quantum mechanics were refined and debated, not through rigid instruction, but through open, intellectual exchange. In Bohr's world, science was not about memorizing equations or forcing conclusions. It was about dialogue, a continuous conversation between minds seeking clarity amidst mystery. Young physicists such as Werner Heisenberg, Wolfgang Pauli, and Leon Rosenfeld found in Bohr not just a teacher but a guiding spirit. His ability to listen deeply, to challenge ideas with gentle yet penetrating questions, and to connect abstract theory with profound human meaning set him apart from his contemporaries. His institute became a home for free thought, where hierarchies dissolved and discovery became a collective act. The air of Copenhagen was charged with curiosity and humility, as if every conversation carried the weight of uncovering the universe's hidden code. Bohr's mentoring style reflected his belief in complementarity. Not just as a principle of physics, but as a way of thinking. He encouraged his students to see opposing ideas not as contradictions, but as partners in understanding. Heisenberg once described discussions with Bohr as swimming in a sea of uncertainty, where every answer opened a new question. Bohr believed that true knowledge was born in that uncertainty, that science's purpose was not to eliminate doubt, but to learn how to live within it productively. This approach shaped the intellectual atmosphere that led to the development of the Copenhagen Interpretation of quantum mechanics, which became the dominant view of the quantum world. Beyond his scientific mentorship, Bohr's humanity set a moral example in turbulent times. During World War II, as Europe was torn apart by conflict and oppression, Bohr stood as a symbol of integrity and courage. Being of partial Jewish descent and deeply opposed to totalitarianism, he was forced to flee Nazi-occupied Denmark in 1943. Smuggled by boat to Sweden, and later flown to Britain and the United States, Bohr continued his work but never abandoned his moral compass. He warned the Allies about the dangers of nuclear weapons and later became a strong advocate for international cooperation and scientific openness. He believed that knowledge should unite humanity, not divide it. Bohr's contributions during and after the war reflected his vision of science as a moral force. After learning about the destructive power of atomic bombs, he campaigned tirelessly for the peaceful use of nuclear energy. He urged world leaders to embrace open-world policies, where scientific knowledge would be shared transparently across nations to prevent future conflicts. Though his appeals were not fully realized during his lifetime, his words planted the seeds for later movements toward arms control and global scientific collaboration. He saw the unity of science as a metaphor for the unity of mankind, a belief that knowledge carries both power and responsibility. His influence also reached into philosophy, shaping how future thinkers approached the relationship between language, knowledge, and perception. Bohr often said, "It is wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature." This simple but profound statement encapsulated his understanding that human observation and language are intertwined with the act of knowing. He inspired not only scientists but also philosophers, linguists, and psychologists to rethink the nature of understanding itself. In his later years, Bohr became a bridge between generations. His institute continued to thrive as a global center for research and education, welcoming scientists from across the world regardless of nationality or background. He remained humble, always aware that even the greatest theories were only glimpses of a deeper truth that could never be fully grasped. His students carried his spirit into the future. Heisenberg, Pauli, and others became leaders in physics, but they always remembered the wisdom and humanity of the man who had guided them. When Niels Bohr passed away in 1962, the world lost more than a scientist. It lost a philosopher of nature, a teacher of wisdom, and a symbol of intellectual honesty. His legacy lived on not just in equations or theories, but in the way science was practiced through openness, collaboration, and respect for mystery. The Niels Bohr Institute continued to serve as a testament to his ideals, a living monument to the spirit of inquiry he embodied. Bohr's life reminds humanity that knowledge, when pursued with humility, becomes more than power. It becomes understanding. His teaching showed that science is not just the pursuit of answers, but the art of asking meaningful questions. His vision of complementarity extended beyond physics into life itself. That truth often lies not in choosing between opposites, but in embracing both sides of the paradox. Through his intellect, compassion, and courage, Niels Bohr left behind not just a scientific revolution, but a moral and philosophical legacy that continues to guide the world toward light, wisdom, and unity. In the aftermath of the quantum revolution, Niels Bohr's ideas began to echo far beyond the realm of physics. His influence touched philosophy, politics, and the human understanding of existence itself. The sixth key chapter of his legacy lies in how his vision reshaped humanity's perception of knowledge, uncertainty, and the interconnectedness of all things. Bohr believed that quantum theory was not only a description of microscopic particles, but a mirror reflecting the limits of human understanding. He often said that every great truth was a statement whose opposite was also a great truth, capturing his belief that reality could not be confined to one perspective. His mind stretched beyond equations, seeking harmony between science and the human condition. Bohr saw quantum mechanics as more than a scientific theory. He saw it as a new way of thinking about the world. The principle of complementarity, his most profound contribution, symbolized that the universe could hold multiple, seemingly contradictory truths at once. Just as light behaves as both a wave and a particle depending on how it is observed, so too could human understanding shift depending on the lens through which it is viewed. This principle went beyond physics and entered the realm of philosophy, suggesting that opposites like order and chaos, certainty and doubt, or objectivity and subjectivity were not enemies but partners in revealing a deeper, unified truth. In the broader scope of human thought, Bohr's philosophy became a bridge between science and spirituality. He never spoke in religious terms, yet his ideas carried a spiritual depth. He showed that humility before nature was the highest form of wisdom. His understanding of uncertainty was not an admission of ignorance, but a celebration of nature's subtlety. He believed that science's greatest gift was not control over nature, but insight into its beauty and mystery. For Bohr, to understand the world meant to accept that some things could never be known completely. This was not a failure but a reflection of humanity's place in the grand design, a reminder that mystery is what gives meaning to knowledge. Bohr's reflections on uncertainty shaped how future generations would approach not just physics, but all fields of human inquiry. He influenced philosophers who sought to understand the limits of language and logic, and he inspired psychologists who explored the boundaries of human perception. His idea that observation changes the observed found echoes in studies of consciousness and cognition, suggesting that the act of seeing the world transforms it. In a way, Bohr had predicted the inseparable link between the observer and the universe long before it became a cultural idea. He showed that reality was participatory, that the mind and nature were partners in creation. His wisdom also guided humanity's moral evolution. After witnessing the destructive power of atomic energy, Bohr understood that science could no longer exist in isolation from ethics. He became a voice of reason in a world on the edge of annihilation, urging nations to embrace transparency, cooperation, and shared responsibility. His idea of an open world, where scientific knowledge would be freely exchanged across political boundaries, was both visionary and urgent. He believed that secrecy and division were enemies of progress, and that only through openness could humanity prevent the misuse of science. Though the Cold War overshadowed many of his appeals, his message became a guiding principle for international scientific collaboration in later decades. Bohr's influence continued to ripple through time, shaping not only how science was practiced, but how it was understood. The principles he articulated became the foundation of new technologies, from quantum computing to cryptography, showing that even the most abstract ideas could have concrete impacts on the world. Yet Bohr himself would likely have viewed these developments with the same calm humility that marked his life. To him, every discovery was only a new doorway, opening to greater mystery. He once said, "The opposite of a shallow truth is false, but the opposite of a deep truth is also true." This paradox captures the essence of his wisdom, that the universe is layered with meaning, and that simplicity often hides infinite complexity. In his final years, Bohr remained deeply contemplative. He welcomed young scientists and thinkers to his home, where discussions about physics often turned into meditations on philosophy and life. Those who met him spoke of his gentleness, his penetrating eyes, and his ability to listen as if every word carried cosmic weight. His home in Copenhagen became a quiet temple of knowledge, filled with laughter, debate, and an unspoken reverence for the mysteries of existence. Even as age weakened his body, his mind remained luminous, a living symbol of curiosity and peace. Bohr's death in 1962 marked the end of an era, but his ideas became timeless. His legacy lives not only in physics textbooks, but in the philosophical hearts of scientists, thinkers, and dreamers who see knowledge as a path toward unity rather than power. He taught the world that uncertainty is not a barrier, but a bridge, that in the very act of questioning, we touch the essence of truth. His vision continues to guide humanity through the complexities of the modern world, reminding us that wisdom lies not in conquering the unknown, but in embracing it with wonder. Through his life, his ideas, and his compassion, Niels Bohr became more than a scientist. He became a voice for the harmony between knowledge and mystery, a light that still shines in the ever-expanding universe of human thought. In the final phase of Niels Bohr's extraordinary journey, his legacy transcended science and entered the realm of humanity's collective conscience. He had become not only a pioneer of quantum theory, but a philosopher of existence, a bridge between reason and reflection. The seventh and last keynote of his life was the enduring impact of his ideas, the way they reshaped modern science, influenced generations of thinkers, and helped humanity understand both the vastness of the universe and the limits of human thought. Bohr's vision did not end with his discoveries. It lived on through the countless minds he inspired and through the moral compass he gave to science itself. As the years passed, the foundations Bohr laid in the early 20th century continued to grow, branching into new scientific revolutions. Quantum mechanics, once a controversial theory debated in the halls of Copenhagen and Brussels, became the cornerstone of modern physics. Every advancement in atomic research, from semiconductors and lasers to quantum computers and nanotechnology, carried within it a trace of Bohr's insight. His ideas about the structure of the atom guided chemistry, biology, and engineering, giving birth to technologies that transformed daily life. Yet Bohr never measured his success by innovation alone. He believed that science's true value was in how it deepened our understanding of nature and ourselves. Bohr's influence also extended into the philosophy of science. His concept of complementarity continued to guide scholars who sought to understand how opposing truths can coexist. It became a metaphor not just for physics but for human experience, showing that life itself often requires balancing contradictions, logic and intuition, certainty and doubt, individuality and unity. Philosophers, theologians, and artists drew inspiration from Bohr's worldview, finding in it a language for expressing the harmony of opposites. His way of thinking taught the world that truth is not linear but layered, not static but evolving, and that understanding comes not from eliminating mystery, but from learning to coexist with it. Bohr's moral and ethical voice also echoed across decades. In the wake of 2 world wars and the dawn of the nuclear age, he stood as a reminder that scientific power must be guided by wisdom. He called for transparency, global dialogue, and the responsible use of knowledge, warning that secrecy and competition could lead humanity toward self-destruction. His open world proposal, though not immediately realized, anticipated the spirit of international cooperation that would later define scientific institutions such as CERN and the United Nations scientific bodies. He envisioned a world where knowledge would be a shared human heritage, not a weapon of division. His dream of openness continues to influence global science policy and international collaboration even today. In classrooms and research centers around the world, Bohr's legacy remains alive. Students learn about the Bohr model of the atom as one of their first steps into the universe of physics, often unaware that behind its simplicity lies a lifetime of deep reflection and courage. His writings, letters, and lectures are still studied for their insight into both the physical world and the human spirit. He showed that science is not merely the study of matter, but the study of meaning, that to explore the universe is also to explore ourselves. His humility, patience, and intellectual honesty became the moral standards by which future scientists would be measured. Bohr's name is now immortalized in the symbols of progress. The element bohrium on the periodic table stands as a tribute to his contributions, a permanent reminder of how his mind transformed the invisible into the understandable. Yet perhaps his greatest monument is not in stone or symbol, but in the enduring questions he left behind. Every time a scientist looks into the quantum world and wonders how particles can be waves, or how observation changes reality, they are, in a sense, continuing Bohr's conversation with nature. His spirit lives in the curiosity that drives humanity to explore the unknown with both awe and humility. In his final years, Bohr reflected deeply on the relationship between science and humanity. He believed that understanding the universe was inseparable from understanding the values that guide us. He once remarked that every advance in knowledge brings new ethical responsibilities, for science without conscience could lead to destruction. He urged scientists to see themselves not as conquerors of nature, but as participants in its unfolding story. To him, knowledge was not a possession but a dialogue, a continuous, living exchange between mind and matter, between question and mystery. When Niels Bohr passed away in 1962, the world mourned the loss of a thinker who had changed not just what we know, but how we think. His funeral in Copenhagen was attended by scientists, philosophers, and leaders from around the world, each recognizing that they had lost more than a colleague. They had lost a beacon of thought. Yet Bohr's legacy could not die. His ideas became part of the fabric of science, woven into every discovery that followed. His belief in complementarity became a timeless lesson, that reality is not one-sided, that truth is complex, and that wisdom lies in balance. Today, as humanity stands at the edge of new quantum frontiers, Bohr's voice still resonates. His teachings remind us that every discovery carries responsibility, that knowledge must serve peace, and that humility before nature is the foundation of all wisdom. He showed that the human mind, no matter how brilliant, is but a participant in a universe vast and wondrous beyond measure. Through his science, his philosophy, and his compassion, Niels Bohr gave the world more than theories. He gave it a vision of harmony between the known and the unknown. His legacy endures as a timeless light, guiding humanity through the ever-expanding horizon of discovery and reminding us that even in uncertainty, there is truth, beauty, and infinite possibility.